In chapter 18, we're going to learn about aqueous ionic equilibrium. Now, we learned about in chapter 16 how equilibrium works. In chapter 17, we learned about acid-base equilibrium. Now we're going to put all of those concepts together and talk about if we have acids and bases together to make buffer systems. And then furthermore, we're going to talk about solubility of ionic solutions. Now, what is a buffer system? A buffer system is either one of the following things. It contains either a significant amount of a weak acid and its conjugate base, such as carbonic acid, and once we remove a hydrogen, HCO3 minus, hydrogen carbonate, or weak base and the weak base's conjugate acid, such as ammonia and ammonium. Now, the design of this solution is to resist the change in pH. So if you have both a weak acid and a weak base in solution, that are related to each other, there's a direct equilibrium associated with them. So for example, we can have the equilibrium of any weak acid, and we'll write carbonic acid's equation as a example. You have your H plus your HCO3 minus. Now, this is an equilibrium, as we know. It's a weak acid. And if we initially have the solution with a large amount, let's say 100 molecules of H2CO3 and 100 molecules of HCO3 minus, we can have a buffer system, because if you add acid to neutralize if you add acid to the solution, what will happen is the conjugate base of H2CO3 will neutralize it. If you add base to the solution, the carbonic acid will neutralize it. So either if you add acid or a base, this solution is a buffer system, which will work to reduce the change in pH or to minimize it up into a certain point, which is called the buffer capacity. Now, this works for both, again, weak acids and their conjugate bases, or weak bases and their conjugate acids. An example that we have in the blood is the carbonic acid bicarbonate buffer system, which is exactly this. So how do we make an acidic buffer solution? Now, you need significant amounts of both the weak acid and its conjugate base. Now, if we just have the weak acid, we know that will dissociate very, very little. But if we add a salt that contains the conjugate base, we can then have equal amounts of both. So the way we can do that is in the carbonic acid bicarbonate system. If we were to make this in a beaker, we could have simply carbonic acid, and we can conjugate the conjugate base, HCO3, hydrogen carbonate, with sodium or potassium or another kind of ion that would make it a salt. So we add both of these solutions into one beaker, we have a buffer system. And they use, for this example, they have acetic acid and sodium acetate. Now, that sodium or that other ion that's not considered part of the buffer system, you can think about it as just carrying the conjugate. So it just carries the conjugate into the solution. Then immediately, since sodium acetate is very soluble, and so is sodium bicarbonate or sodium hydrogen carbonate, what will happen is the ions will just dissociate. And then in solution, you'll have exactly this, as you see here. You'd have the weak acid, the conjugate base, H3O plus, and Na plus. But the H3O plus and Na plus don't really contribute to the buffer system, because what's doing the neutralizing of the acid that is entered into the buffer system is going to be the conjugate base. And what's doing the neutralizing of the base that's added to the buffer system is the acetic acid. So here's an example of what happens when you add a strong base to the acidic buffer system. And when you add a base, what's going to happen is the acid will then neutralize it. And even though you don't have many molecules, or you have a lot of molecules of the acetic acid, what will happen is the base is going to be strong enough to where it kind of rips the hydrogen off of the acetic acid. Because if you remember from last chapter, the strength of an acid is determined by how strong the bond is between the protonatable hydrogen and the anion. So if you have a weak bond like acetic acid does, a strong bond like acetic acid does, you're going to have a weak acid. But if you have something else that is in the solution, like a strong base that really, really wants a hydrogen, like NaOH, it will grab that hydrogen even from a weak acid almost all the time. And it will then become neutralized itself into, like, by this equation. If we add a strong acid, the same thing will happen, but with the conjugate base component of the buffer system. So the HCl will then, the hydrogen will come off because it'll be immediately ionized, and then that will bond to the HC2H3O2, which is the acetic, to create acetic acid from acetic acid's conjugate base, or just the acetate ion. So we basically went over how that works. Now, which solution would be a buffer system? Remember, it's either one of the following. It is the weak acid and its conjugate base, or the weak base and its conjugate acid. And out of these, D is the only one that has that. So you have HNO2, and then you have NaNO2. And remember, Na is just the carrier ion for the NO2. So we can basically, Na comes off immediately when you put it in a solution. Now, the common ion effect is very important for buffer systems and very important for solubility, which we'll get to later in the chapter. But it basically means if you have an equilibrium like we do down here with HNO2, which is nitrous acid, and its conjugate base, if we add more of this conjugate base, what will happen is it'll shift the equilibrium to the left because they're common ions. So if you have, let's say, a solution that has, it really takes precedence in precipitation reactions, where we have a precipitate on one side and then the aqueous on the other side. If you add more of the aqueous ion, more precipitate will form. And you kind of direct the direction of precipitation. Now, we can find the pH of buffer solutions just like we did for normal acidic or basic solutions with the pKa, the Ka, the Kb, and all that good stuff. And we're going to introduce a new equation having to do with buffers. And this is called the Henderson-Hasselbeck equation. Now, this will be given to you on the exam. And this only works, well, it works a lot of the time. And it works especially when X is very small. So X, remember, for your ice charts is going to be related to the amount in molarity of change, right? So it's either plus X, plus 2X, whatever. So that's going to be your amount of change. And if that amount of change is very small in comparison to your Ka, when Ka is small and we have large concentrations, that is when X is going to be. So how do we know to use the Henderson-Hasselbeck equation? Skip to the bold. Initial acid and salt concentration should be over 100 to 1,000 times larger than Ka. So if you have Ka, anything that's 10 to negative fifth, 6, 7, 8, you can basically use it, right? But if you have very low concentrations as well, you have to check it out. So if you have over 100 to 1,000 times, so that's 10 to the 10 squared difference or 10 to the third difference or more between the acid and salt concentrations and the Ka. Just keep that in mind. Here's an example. We'll go over that in class. So we can use ice charts to calculate the change in pH when you add either an acid or a base to the solution. So if you have added acid, it reacts with the conjugate base to make more of the acid. If you add base, it reacts with the acid to make more of the conjugate base. So based on what you're adding, you know which way the equilibrium is going. Now for this problem, for calculating the pH of any buffer solution, we can just throw it in the Henderson-Hasselbeck equation. But when we make the change, that's when we have to use the ice chart, meaning when we add acid or base to the buffer solution. So the Henderson-Hasselbeck would be pH equals pKa plus the log of the base over the acid. Now, the pH equals pKa, and we're given the pKa for acetic acid, which is 4.76, plus the log of the base, meaning the conjugate base over the acid. So the conjugate base in this case is going to be the 0.1 molar sodium acetate, 0.1, divided by the acid, which is 0.1. 0.1 divided by 0.1 is 1. Log of 1 is 0. Therefore, your pH equals pKa. which is equal to 4.76. Now, this tells us a lot. This tells us that in a buffer system, if we have the same amount of acid and conjugate base or base and conjugate acid, the pH is equal to the pKa of that conjugate, of that acid. Or the pOH is equal to the pKb of the base. So that's a very important definition to have. And we're going to see that later on when we get to titrations. Here's another example. Calculate the pH of this buffer system, and we can also use Henderson-Hasselbeck. Or we can use the ice chart as well. Either one will work. That's what a buffer does. Basic buffers. Now you can have buffers that also consist of weak bases and their conjugate acid. And remember this weird looking F, that just means an equilibrium. Should be double arrow. And they work the same exact way. Now, if you have a buffer that contains an equal amount of a weak acid and its conjugate base and has a pH of 5.25, which would be reasonable pH value after the addition of a small amount of acid. So if you remember a buffer, it mitigates the change in pH. So it should be a little bit lower than 5.25. So 5.15 is a good estimate. Now, buffer effectiveness. We have buffer capacity, which is the amount of acid or base that the buffer can neutralize, and the buffer range, meaning in what pH range is the buffer effective. pH ranges, they vary in different buffer solutions. If you have a weak base and a conjugate acid, its buffer range is going to be higher than a weak acid and conjugate base because they operate at a lower pH to begin with than the base buffers. So the buffer will be most effective when the ratio of acid to base is 1. And it's effective basically in the ratio of base to acid of 0.1 to 10. So keep that in mind as well. And if you have a larger amount of acid and base in general in the buffer system, it'll be a more effective buffer because then it can neutralize physically more molecules. Now, generally speaking, the 0.1 to 10, if you remember, the pH is a log, right? The log of concentration. So it's a base 10 unit, meaning that the ratio of acid to base, if it's 10, it'll be the maximum effectiveness, or if it's 0.1, it'll be the minimum effectiveness. Now, the pH of 10 is 1. Or sorry, the log of 10 is 1. Therefore, we could say the buffer range is, of the lowest pH of a buffer is the pH equals the pKa minus 1. And the highest pH possible is the pKa plus 1. So the effective range of any buffer, we can say, is the pKa of that weak acid plus or minus 1. That's the range. So that's very important. So the buffer capacity is the amount of acid or base that can be neutralized without causing a large change in pH. And we can determine that from titrations. Now, a titration is when you have an unknown concentration of something that is of a solution, and you have something of a known concentration that you're adding to it. In acid-base titration, we add an indicator solution, which is a chemical that changes color when the pH changes. And if you add enough base to an unknown acid, eventually the color will change, and that marks the point at which the base neutralizes the acid, otherwise known as the equivalence point. So here's how titration works. So you begin the titration, you have an unknown amount of acid, you're adding base, you add the base, and then you reach the equivalence point. And this equivalence point means that it's neutralized. Then you can have a titration curve. So the equivalence point is kind of the point of inflection of this titration curve, meaning that is when the base completely neutralizes, stoichiometrically neutralizes the acid or vice versa. And it depends. The equivalence point is not always 7. If you have acidic or basic salts, then the equivalence point varies. It could be of an acidic salt, the equivalence point is less than 7. A basic salt, meaning the conjugate, meaning let's say we have a base buffer system, it would be greater than 7. So there's the equivalence point. Here's where we would see, let's say we have a titration with a strong base to a strong acid. In that case, the equivalence point will always be 7 because there's no spectator conjugates around because it's complete dissociation all across the board. So you can see the pH of the strong acid is going to be very low. Then when you're adding the NaOH, eventually reaches a point where it changes drastically in pH. This will happen over a couple of milliliters, and you'll see the point of inflection is going to be 7. That's where the equivalence point is, and where you'll see a change in color. And then with strong base or strong acid is just the opposite. But then when you have titration of a weak acid with a strong base, this is where, and in vice versa, is where it gets a little bit confusing. It's important to remember these bullet points, and I'll just read them. The initial pH is obviously determined by just the weak acid. That's all you have. The pH on the bottom, meaning of the excess acid region, meaning right here, is determined by a buffer system, right? So in that case, you make your ice table of the acid, and then you're adding whatever base, and you're kind of just using the dissociation, and then you're adding the base to find the pH. Then the equivalence point, you're using the pKb of the conjugate base. And the way you find pKb from pKa is 10 to the negative 14 divided by pKa. And then after that, you have a lot of strong base, which you can use to find the pH. So here's an example of a titration of a weak acid with a strong base. You have the weak acid adding base slowly. You're going to have a jump in pH. And the equivalence point is going to be represented by the weak conjugate base amount. Because at this point, every single acid molecule of the weak acid is now dissociated because it was titrated with a strong base. What's going to be remaining from that weak acid is going to be its conjugate base. From that conjugate base amount, we can determine the pH using in the Henderson-Hasselbeck equation. And then after that, you add more of the base, the strong base, you're going to have an excess in OH minus, which you can use to figure out that. So we'll do these examples during class. And then titrating a weak acid with a strong base. And here's something that's important, the half equivalence point. So the equivalence point is right here. There's actually a thing called the half equivalence point where the pH is equal to the pKa. Now the pKa, what that means by definition, when pH equals pKa, we saw that before, is when the log of the base over the acid is equal to 1. When it's equal to 1, that means the amount of weak acid is half dissociated. So around here, it's going to be half dissociated. Full dissociation is right here. Half dissociated is right here. So that's where the concentrations in the solution of the weak acid and the conjugate base will be equal. So that's where pKa equals pH is at the halfway point. There's more examples. So conceptual question. The titration, or here we have two 25 milliliter samples of unknown monoprotic weak acid, and A and B are titrated with 0.1 molar of NaOH. The titration curve for each of the acids shown below. Which of the two weak acids is more concentrated? Whichever acid is more concentrated, it'll be the one that requires the most amount of base to neutralize that amount. So if you look at acid A, it takes over 30 mils to get to the equivalence point, 35 mils or so. of the base, meaning that's how much, that means is a directly more molar amount of acid than there is in acid B. So that's our answer right there. Next one, which of the two weak acids has a larger Ka? So large Ka, that means a larger amount of dissociation. So which one's stronger is basically what it's asking. And whichever one's stronger, well, if we have the same concentration, or we don't have the same concentration, but we have the same amount, the one with the lower pH initially is going to be the one that's stronger, right? Because there's the more dissociation. And dissociation is marked by a larger Ka. So that would be acid B. Then for titrations of weak bases with strong acids, it's basically the opposite. So you start off at a high pH, your equivalence point is right here at the inflection. The halfway is where the pH equals pKb. Or, I mean, pH equals pKa as well. Not pKb. It would be pKa of the weak base, which would be essentially pretty high. So what is the pH of the half equivalence point in the titration of a weak base with a strong acid? And the pKb of the weak acid is that. So if we know that at the half equivalence point, pH equals pKa, the relationship between pKa and pKb is 14 minus pKb equals pKa. So 14 minus 8.75 is 5.25. Now, if you have a titration of a polyprotic acid, you're going to have more than one equivalence point. So you can read this on your own. I don't want to spend too much time. If you monitor pH during a titration, there's different ways to do it. We have experimentally, we can use a probe and we can use the indicator. So phenolphthalein is an indicator which changes color in a certain pH range. So around pH of 7 or 8, you'll start to see the color change. That's when the equivalence point happens. And then the color will get darker as you add more. And there is different types of indicators. So there'll be a part 2 to this video going over solubility equilibrium, but that's it for part 1. So stay tuned.